Hello, welcome back to one of the most important lessons in all of chemistry. In this lesson, we're going to learn about ionic compounds. So we have two broad classes of compounds in chemistry, or bonding in chemistry. One is called the ionic compounds, and the other is called the covalent, or the molecules, right? So we've talked about molecules before, and those are water and carbon dioxide and what that entails. Here, we're focusing on the ionic compounds, which are just as important. So you have experience with those as well. Table salt, sodium chloride, that's an ionic compound. There are many others, and what we're going to do in this lesson is we're going to learn how to take two elements off the periodic table that we know are going to bond in an ionic fashion, and we're going to be able to write down their chemical formula based on knowing the charges on the ion. So it's several steps, but we've already built those steps in past lessons. We'll build upon that here. We're going to pick two elements off the periodic table and be able to write down the chemical formula for what they should produce as a compound. So when I talk about ionic compounds, what we're talking about is a metal plus a non-metal. Remember, the diagonal red line here separates the metals, which are on the left of the periodic table, and with the non-metals on the right. Now, the exception to that is hydrogen is actually a non-metal, even though it's written on the left-hand side of the table because it's the lightest element. It behaves mostly as a non-metal. The reason hydrogen is over there is because sometimes hydrogen can gain electrons and sometimes it can lose electrons. It can kind of behave both ways. But most of the time in chemistry, with things that we're talking about, it's going to be more like a non-metal over here. So when we take something from the left plus something from the right, that is what we call an ionic compound is what is formed. Now, a little bit of review. What we've talked about in past lessons is that when we have items on the periodic table, we can predict the ions that we think they will form based on the following. Over here in the right-hand column is the noble gases. These have a very stable electron configuration. They don't like to react because the electrons are very stable in the orbits and the shells that are there. Now, I'm throwing around terms, but when we get to electron configuration, we'll understand much more concretely why the noble gases are stable. For now, just remember that they are stable, and when I say they're stable, I mean the outermost electrons, the electrons that participate in chemistry, are basically fully filled and fully stable. So they don't like to be transferred or shared. But the elements right next door to the noble gases are always trying to obtain a electron configuration in the outer electrons that is closest to its nearest noble gas because that is the most stable. So this chlorine is always going to try to gain an electron to have as many electrons as argon. The fluorine will try to gain an electron to look like neon. The oxygen will have to gain 2 electrons, and the nitrogen will have to gain 1, 2, 3 electrons to look like its nearest noble gas. So the elements are trying to look like its nearest noble gas neighbors. Now, why is that the case? Well, it comes down to the electric force being so strong. And when I get to electron configuration, I can explain more fully why the noble gases are so stable and therefore why the elements are trying to get as many electrons as a noble gas. So these over here, the nonmetals in general, are trying to gain electrons to be like their noble gas neighbor. Now over here on the left-hand side of the table, these elements theoretically could try to gain electrons to look like a noble gas, but that's a lot of electrons. Sodium would rather lose an electron and look like the nearest noble gas, which is neon. Neon has 10 electrons, but sodium has 11. It would be easier for sodium just to lose an electron. So when I say sodium wants to do this or wants to do that, it doesn't want anything. It's just that the outermost electron of sodium, we're going to learn later, is not very tightly held onto by the atom. So instead of gaining a ton of electrons to look like argon, it's going to be more energetically favorable to just lose its outer electron, therefore going from 11 electrons down to 10 and looking like a more stable electron configuration. And the same thing's going to happen with potassium. It's going to energetically prefer, quote unquote, to lose an electron and look like argon. And so calcium, instead of losing 1, it will lose 2 and again look like argon. So elements in this column generally tend to lose an electron, with the exception of hydrogen. Hydrogen can lose or gain electrons. It's kind of the oddball. In general, they like to lose 1 electron. These guys like to lose 2 electrons. These guys like to gain 1 electron, and these guys like to gain 2 electrons. So with all of that out of the way, now we can look at the periodic table. We can identify what ion is going to be formed by those elements, and then we can predict what compound will form ionically. One more thing I'll say before we do the problems. All of the other elements in the middle of the periodic table, not near the edges, near the noble gases, they form ions also, but they're a little bit unpredictable in the sense that we don't know ahead of time exactly what they'll form. There may be 2 or 3 different ions that, for instance, lead or iron might form, and it's going to depend on the compound that's there. So you can predict what's going to happen, but you're going to be less certain about what's going on when the elements are in the center of the table. But when you have a metal way over here on the left and a non-metal on the right, you can very accurately predict the charges and the compound that will result. So what we basically have said is that for ionic bonds or ionic compounds, what you have is a metal, which is on the left of the table, plus a non-metal. Right? We're going to learn in a second that this is called an ionic bond that forms. And because of the way the electrons are working, the electrons are transferred from one to the other, from one species to another. Because remember, if sodium, for instance, likes to lose 1 electron and chlorine likes to gain 1 electron, what's going to happen is after the electron, if sodium likes to lose an electron or is energetically favorable to lose an electron, the electron will leave the sodium and then just jump to the chlorine because the chlorine energetically wants to grab an extra electron. So then what's going to happen is they're going to bond together because the sodium is positive and the chlorine is negative, and they're going to attract each other. But the electron has been transferred from one atom to another, and that's why it's called an ionic bond, because when the electron is transferred, you have ions left over, and those ions then attract each other. Now, I'm not going to write it on the board, but let me contrast that to what I've already taught you about molecules. Molecules are different. Ionic compounds do not form molecules. I'll show you why in just a second. But in molecules, it's a little different. It's instead of metal plus non-metal, it's 2 non-metals for molecules. Think about carbon dioxide, 2 non-metals. Sulfur dioxide, 2 non-metals. Even water, H2O, because hydrogen behaves like a non-metal. Those are all covalent bonds, which don't transfer the electrons, they just share the electrons. So they're not like electron going from one to the other, they're literally shared between the elements, and that's something we'll talk about a little bit later. So that's a compare and contrast. So the broad classifications are ionic compounds and molecular compounds. All right, so now we're focusing in this lesson on just the ionic compounds, right? So let's take our famous sodium, and we're going to combine it with chlorine. So we have sodium, we're going to combine it with chlorine. Elemental sodium, just an element of sodium and an element of chlorine. So write it down like this, and underneath that, let's go ahead and write what the ions would be. Now, sodium, as we said many times, is in column number 1. It's going to want to lose an electron to have a stable electron configuration like neon with 10 electrons. So once it loses that electron, sodium is going to have a positive charge of +1, so we put a positive there. Chlorine is going to do exactly the opposite. It's going to gain an electron to look like argon, and so because of that, it is going to have a -1 charge. So after the electron is transferred from sodium to chlorine, this is what we're going to have. We'll have an ion of sodium and an ion of chlorine. All right, so what we do after we write that down is, what's going to happen is the sodium is positively charged. The chlorine is negatively charged because the electron, remember, has been transferred. So we have 2 ions, opposite charges. Opposites attract. The sodium ion, the chlorine ion will be attracted to each other and bond together because of that attraction. Because the attraction comes from ions and from ion charges, it's called an ionic bond. That's totally different than what's going on in water. In water, which is a molecule, a covalent bond, the electron's not transferred. They're just shared between the hydrogens and the oxygens, and it's a little bit different. It's actually quite a bit different. The ionic bond, very, very strong, and the electric force is so strong to pull those things together. All right? Now, what we do to predict what kind of molecule is going to form is basically, this is like a +1 and this is a -1. So you do a little crisscross here, and you drag that the +1 down here and the 1 here. You ignore the signs for a moment, and what you say is that sodium will have, this is a 1, -1. The 1 goes down here, so sodium has a subscript of 1, and then this +1 goes down here. Cl1. So what you do to figure out what compound is formed is you ignore the signs and you take the numbers. 1 goes down here, 1 goes down here, sodium 1, chlorine 1, and when you have 1s, you can drop them and you can say NaCl. This is what is going to be formed. Now, what is actually happening here? What's happening is because sodium has an ion, it lost 1 electron. It has an ion charge of +1. And chlorine has a charge of -1. Because they're equal and opposite charges when they attract each other, see, everything wants to be neutral in chemistry. Everything wants to get neutralized. So the overall compound here wants to have a neutral charge. The way to do that is for 1 chlorine ion to bond with 1 sodium ion in a 1-to-1 relationship. Then the overall charge of the unit there is 0. That's why they bond in a 1-to-1 way, and that's why the crisscross thing works. Because what it's basically telling you is the ratio of 1 sodium and 1 chlorine, because I have 1 sodium with a charge of +1 and 1 chlorine with a charge of -1, this is the proper ratio. In other words, it would never be Na2Cl, because then if I would have a total charge of +2, I'd have 2 sodiums +1 charge, a charge of +2, and then I would have a -1 charge, and that wouldn't be neutralized to 0. Everything in chemistry wants to, if it can, neutralize, become neutral, all right? Because the electric force is so strong. Remember, I keep telling you, everything comes down to the electric force. If anything was ever out of whack, if this thing bonded in such a way to have an overall charge, all it would do would attract something else, some other ion to it, to bond with it and to neutralize it again. So everything wants to be neutralized because the electric force is so strong. Now, to visualize what's happening here in the ionic bond, I want to show you this picture. So now we're not looking at the periodic table, we're looking down below. So what really is happening is the red balls here are positively charged ions, and the blue and the green ones here are negatively charged ions. And so what they're doing is they're bonding in a 1-to-1 ratio, but what's happening is it does not form a molecule. That is probably the biggest misconception. People think NaCl is like a molecule. It's not a molecule. And the reason it's not is because it's an ionic bond. What happens is the sodium and the chlorine bond together, but this sodium can attract another chlorine which gets stuck to it. And then this chlorine here can attract another sodium which gets stuck to it. And then this sodium can attract another chlorine which gets stuck to it. And it ends up forming a lattice, which is a regular repeating lattice where every one of these sodiums attracts another chlorine. But if you pick any one in the center, it's always bonded to an equal number of the opposite thing. So overall, it's still a charge, a net charge of 0, because if you count these guys, if you carve out a bit of it and count the number of ions, you'll always get an equal and opposite number of chlorines to sodiums. But the lowest whole number ratio is still 1-to-1. Right? So you may, if you could zoom in on a microscopic sample of this, you would see maybe in a sample under a microscope, maybe 100 chlorines ions and 100 sodium ions all bound together in a lattice. So you might think that the ratio or the formula would be sodium 100, chlorine 100, 100 sodiums to 100 chlorines. But what you always do, remember, for the empirical formula is you divide and simplify it to the lowest ratio. So depending on how much of this thing you look at, you could get equal number of chlorines and sodiums, but the lowest whole number ratio is 1-to-1. That is why we write it as sodium chloride, NaCl. It does not mean that there is a molecule of sodium chloride that is floating around together like a water molecule does, right? Water molecule is totally different. It's not an ionic bond in a water molecule. It's covalent bonding, which is a sharing of electrons. It's totally different. The reason sodium chloride behaves differently in all ionic compounds, with few exceptions, they form this 3-dimensional lattice, which if you look at salt crystals, you can see the shininess. That's what's going on here. It's a regular repeating pattern of sodium and chlorine ions bonded together, where the lowest whole number ratio is 1-to-1. We call that 1-to-1, that lowest ratio, we call it a formula unit. So when you're doing ionic bonding and you get, some NaCl, for instance, I don't want you to think of it as a molecule floating around. I want you to have that picture that I just showed you in your mind of a lattice of them, where there's tons of sodiums and chlorines all stuck together in a regular repeating pattern, kind of like putting oranges into a crate or something like that. Oranges alternating with apples, let's say. But the fundamental ratio of sodium to chlorine is 1:1 in this case. All right, let's move on to the next one, and we will see how that might change. Let's take a look at the element barium, and we combine it with the element of chlorine. So all we have done is changed what the metal is. So if we look back at the periodic table, to barium, we see barium is down here. Now barium, when it forms an ion, likes to lose 2 electrons. It loses 2 electrons in order to look like a noble gas. So at the very next step, what you do is you say, all right, barium likes to form an ion of +2 because it loses 2 electrons. Chlorine is always going to want to accept only 1 electron. Sorry about that, chlorine with the negative sign out there. Chlorine is always again trying to gain 1 electron. So these things want to attract each other, right? Because this is a positive charge and this is a negative charge. But when they attract each other and form the lattice, they always want to have an overall neutral charge, right? So what you do is you do a crisscross down here, and this 2 goes down here, and the 1 goes down here, and what you'll be left with is barium has a coefficient now of 1, and chlorine has a coefficient of 2, but you don't ever write the 1s in the I said coefficient, I meant subscript. You just drop that. So BaCl2 is the answer to this formula unit. So this is what you would write down. So if somebody asks you what compound would form if barium combines with chlorine, what you do is you find the charge barium likes to form from the periodic table, the charge chlorine likes to have when it gains electrons from the periodic table. Opposites attract, so these guys stick together in an ionic bond, but they don't stick together in a 1:1 ratio. Why? Because if I had 1 barium and 1 chlorine stuck together, if it was just a 1:1 ratio, I would have an overall charge of +1. I would have a charge of +2 and -1. If I did 1:1, it would have an overall charge of a positive. So you see, if I ever had that situation where they bonded 1:1, then it would have an overall charge, and it would just attract something else, which would try to neutralize the charge that was there, and it would keep attracting stuff until there was no more net charge. So what happens is it really bonds in the ratio of 1 barium to 2 chlorines. 1 barium has a +2 charge, each chlorine has a -1 charge, so overall you have a +2 and a -2. This is a neutral formula unit, right? So if I don't have a picture of it, but the sodium chloride was bonded in a ratio of a fundamental ratio of 1:1, but in the barium chloride, it would be, if you could zoom in on it and look at it, it would be in a fundamental ratio of 1 barium to 2 chlorines. That would be the repeating pattern all throughout the lattice, 1 barium to 2 chlorines. If you zoom out, of course, you could see more bariums and more chlorines, but the fundamental ratio, the empirical formula, also called the formula unit, I'll put it down again, formula unit. The formula unit would be BaCl2. So here's where I want to pause, and since we kind of know the general idea, we're going to do more problems in this lesson, we are. But I need to pause and show you something else very important. So we talked about the idea that this is ionic bonding. So it's anytime you have basically 2 opposite charges that are coming together and bonding because of the ion charge, that's called an ionic bond, right? So what I need to do, I think at this point, is reveal to you some common ions. So this is a very busy board, okay? You do not have to memorize this. So if you're learning this for fun, then you can use what I have written here. If you're taking a class and you have a textbook, any textbook is going to have a table of ions. And some of them we already just get from the table, but some of them are new. So what I want you to do is kind of read this with me. I'm going to go over it real quick. I'm going to explain why we have it. We're going to use it as we go farther along and do more problems, and we'll refer to it throughout the next several lessons. But if you have a textbook that has a longer list or a shorter list, that is fine. This is not an exhaustive list. It's just to get us started. All right, so it's broken into cations, which are positive ions, and then we have the anions at the bottom. All this thing is saying is that some very common cations are listed here. It is not an exhaustive list. So what we have is H. when it loses an electron, it has a positive charge. We call it a hydrogen ion, right? And you can see this from the periodic table, if it were to lose its only electron, it would have a positive charge left over. We just call it a hydrogen ion. Lithium and sodium and potassium, if they lose a single electron, they're going to have a positive charge left over. So lithium, sodium, potassium. Lithium, sodium, potassium. Notice I told you that everything in the first group likes to lose one electron. So this table is really kind of like spewing out what I've already told you in words, that you can predict the charges oftentimes from the positioning on the table. So these things we would have already predicted just by looking at the table. Cesium, where is that at? CS is cesium. Cesium again is here. We can predict from the chart, from the periodic table, it's going to lose one electron, so it's going to have a positive charge. So this is basically called a lithium ion, a sodium ion, a potassium ion, a cesium ion. Now here is silver. This one's different. Silver is not in the first couple of columns. Silver is in the middle of the table. Where is silver? Right here. Now I told you, things in the middle of the table, you can't predict very easily what charge it's going to have. So what often happens in the center of the table with those metals is those metals, they're almost always going to want to lose electrons, but sometimes they'll lose 2 electrons, sometimes they'll lose 3, sometimes they'll lose 4. It depends on what they're bonding with. And you can't predict ahead of time. It comes from experience, okay? So I'm just telling you that silver, since you can't predict it from its location here, like how would you count? How many will it want to lose? I'm just giving you a table to get you started that in general, silver is going to want to lose a single electron. Now, can it do other things? Yes, but this is a silver ion that's very common. All right? Now, we need to handle something that's also very important that we have not mentioned up to this point. There are groupings of elements that like to kind of band together as a group, and they form ions, and they're called polyatomic ions. Now, I do not expect you, nor should anyone expect you at this point in your chemistry career to predict what polyatomic ions will happen. But we're not predicting anything. I'm just giving you a list and telling you that these are polyatomic ions that like to band together, and they have an overall ionic charge. And they behave and participate in bonding as a unit. So it turns out that NH4, when they come together, they have an overall charge of +1, and this configuration is called an ammonium ion. Ammonium ion. All right, that's the only one in this list that's a positive ion. When we have the negative ions, they have a whole lot more negative polyatomic ions. You know, the sulfates and the nitrates and others that are very common, right? But these are all a general class where atoms are grouping together and they have an overall charge. In this case, ammonium, NH4, has an overall charge of +1. You are not supposed to be able to predict why it has a charge of +1 right now. Later on, we're going to show and understand why these polyatomic ions have the charges they do. For now, just know that some atoms get grouped together, they energetically favorably group together and have an overall charge, and they can participate in ionic bonding in the way in which we're doing it here. And so we're going to use that. All right, let's move on. So copper can have a +1 charge, but notice down here that copper can also have a +2 charge. So this is an example because copper is in the center of the periodic table. Copper is right here. I told you the things in the middle are a little bit unpredictable. So it turns out that copper can have a +1 charge if it loses 1 electron, but it can also have a +2 charge if it loses 2 electrons. So we write them as copper plus, copper 2 plus. But in words, we call it copper 1 and we call it copper 2 ion. Because when we name these things, we're going to be naming them and putting words down. So sometimes we have to say copper 1 or copper 2 to indicate which ion of copper we're talking about. With oxygen and with fluorine and iodine, things that we always know the charge is almost always going to be whatever it is, we don't have different variations. But with the metals like copper and nickel and lead and iron, they often have multiple charges. So that's why we have here, we have the magnesium, calcium, strontium, barium, zinc, cadmium. Where do those live? We have magnesium, calcium, strontium, barium. And there's beryllium here as well, but that's not a common one, so we don't list it there. But notice that they're all in group number 2. So magnesium, calcium, strontium. Magnesium, calcium, strontium. And then we have barium. And so basically all of these come from group 2. So we would have been able to predict that they have a positive 2 charge just from their position on the table. But we have zinc, which is in the center of the table as a metal, and we have cadmium, Cd. And where is Cd at? There's cadmium right there. So it's a metal right there, and it's a little unpredictable because of that. And you can see that zinc is also in the middle of the table as well. Where is zinc at? Zinc is right there, right above cadmium. So they're in the center of the table. So again, they often form different ions, but these are the most common ones. So zinc generally forms a +2, cadmium generally forms a +2. Cobalt is in the center, also generally forms a +2. Copper forms a +2. We call it copper 2 to denote it differently than copper 1. Iron can form a +2, so we call it iron 2. Then that's to differentiate it from iron 3, because iron can lose 3 electrons or it can lose 2 electrons. Manganese can lose 2 electrons, but we denote it manganese 2 because there are other ions of manganese as well. Nickel can have a +2, lead can have a +2, tin can have a +2, and we call them the same thing, nickel 2, lead 2, tin 2. Now mercury is a little bit weird because we have a +2 ion, we call it mercury 2, but we have another +2 ion, but notice it's Hg subscript 2. So there's 2 mercury atoms together. Overall, it has a +2 charge. We call this mercury 1 because really, if you think about it, if you have 2 things together and overall there's a +2, then it's almost like each mercury atom has a charge of +1. So we call it mercury 1. Now, don't get bogged down in the minutia of this, all right? That's why I tried to do a couple problems earlier, just to get us going. Overall, what you're doing is when the atoms on the periodic table are near the edges, in the main group elements, you can often just predict what ions are going to form, and then you can do the crisscross, and you can predict what compound it's going to make, what ionic compound is going to form, which is going to look like a 3-dimensional lattice, which is what we showed a minute ago. But ionic compounds can form with these metals as well, because these metals can lose electrons. Think about it, metals conduct electricity well. The electrons are easily able to be kicked out. So they do form positive ions, so they can ionically bond as well. But the problem is that metals can sometimes lose 2 electrons, sometimes lose 3 electrons, sometimes lose 4 electrons. And to differentiate from that, we're just saying that iron commonly forms a +2 ion, but it also forms a +3 ion, and we differentiate that by saying iron 2 and iron 3, and so on. So these are just the common ones. There are other ions that can form. A lot of elements can form 4 or 5 different ions, but some of them are just really energetically unfavorable, so you don't often see them, especially in introductory chemistry class. Now, all of that was to talk about cations. I mean, that's just half the list, right? Now we have the anions. And here we have the easy ones, right? Hydrogen can go either way, so we can have a negative charge on hydrogen. We call that hydride, right? Fluorine, when it forms a negative ion, we call it a fluoride. Think about fluoride toothpaste. Then you have chloride, bromide, iodide. Now these are all from the halogens, fluorine, chlorine, bromine, iodine. And so we can predict from the table that these are going to gain 1 electron. So this is just showing in table form that these elements can gain 1 electron. Now hydrogen, of course, can gain an electron, but it can lose an electron, so it can go either way. All right? Now, the rest of the things on the list are more polyatomic ions that have an overall negative charge. So carbon and nitrogen can come together and have an overall charge of -1. It's called a cyanide ion. Oxygen and hydrogen, just one of each, can come together and have an overall charge of -1. It's called a hydroxide ion. Then you have the chlorates and the perchlorates and the acetates and the permanganates. So one manganese there with 4 oxygens overall as a unit has a charge of -1. The nitrate, extremely common, NO3 has an overall charge of -1. You are not expected to know why these have the charges they do. You're not. We're going to talk about it later because it has to do with electron sharing. Notice that all of these are coming from the right-hand side of the periodic table. So they're all sharing electrons, and later we learn how to predict the charges on these polyatomic ions. All you need to know is that they exist and that they're stable and that they're common. Right? Then we have the oxide ion. Oxygen wants to gain 2 electrons. We know that from its position on the table, so there's nothing new there. But you can have O2 with a -2 charge. We call that a peroxide ion. Think about hydrogen peroxide, H2O2, right? And then you have sulfide that has a charge of -2. -2, we can predict that from the position on the table, but we have these other polyatomic ions. CO3 has an overall charge of -2, that's called a carbonate. CrO4 has an overall charge of -2, it's called a chromate, and then you have a dichromate, which is similar. Sulfate, extremely common, SO4 has an overall charge of -2. And then finally we have nitride, and then we have phosphate, PO4, -3. So these are not things you need to memorize. But I do want to say, if you haven't noticed, that the negative ions all have IDE in them. Or the polyatomics don't always, but the elements do. Fluoride, chloride, bromide, iodine. I didn't write them down, but that's what they're called. And then we have hydroxide, and then we have oxide and peroxide. So it's going to be very common when we name compounds. That's why you hear about iron oxide being rust, because the negative charge gets an IDE in its name. All right? So I had to wedge this in somewhere because you have to learn about polyatomic ions. You do not need to know why they form together. You do not need to know why they have the charge they do. What you do need to know is that they exist and that they can bond with other things. So that was our intermission that we had to do. I wanted to get through a couple of problems first. And then the next thing I want to do is I want to erase unit, put it down here to give me some room. I'll do the same thing down here to give me some room. And then we'll continue. All right, let's continue on and see if we can predict what what the chemical formula will be for some of these ionic bonds that we have. So let's say that we take magnesium and we'll combine it with nitrogen. So the first step is to see what charge will magnesium want to take. Magnesium is here, it's going to want to lose 2 electrons, and so it's going to have a charge as an ion of +2. So you put 2+ right there. Now nitrogen, it is going to want to gain 1, 2, 3 electrons, and so it's going to have an overall charge as an ion of -3. Okay? Now the next thing you do, once you write the charges down, you just say, okay, you do crisscross, this goes here and this goes here. And so what you're going to be left with is magnesium will have a subscript of a 3, and nitrogen will have the subscript of a 2. So Mg3O2, and this is the lowest ratio. I can't reduce this anymore, just like I can't reduce sodium chloride 1:1. So this is what we say the formula unit is. Formula unit, right? Which is the lowest whole number ratio here. Remember, it's really a 3-dimensional lattice where 3 magnesium atoms are kind of bonded for every 2 nitrogen atoms, but in a 3-dimensional fashion as a crystal lattice there. That's basically what's going on. And the reason why this ratio works is because if you have 3 magnesiums, each with a +2 charge, this is going to give you an overall charge of +6. And then if you have 2 nitrogens, each with a charge of -3, then again you'll have -6. So you'll have a +6 from the magnesium contribution and a -6 from the nitrogen contribution. Overall together, it'll be a 0. And that's what things like to do when they bond. They want an overall 0 because the electric charge is so strong that they're going to keep attracting stuff until the charge is overall 0. That's why they bond in this ratio. Now let me give you a cautionary tale. We need to do one more to show you when something different might happen. Let's take titanium and bond it with oxygen. Now, we don't know the charge on titanium, so I'm going to tell you that the charge on titanium is 4+. That means it loses 4 electrons. And oxygen, we already know, wants to gain 2 electrons. You can see that, oxygen wanting to gain 2. Titanium is way over here, so you're not really sure what it, because it's a metal in the middle, you're not sure what it wants to do. I'm telling you here that it does want to, in this case, lose 4 electrons. So we do the crisscross like normal. And what we see is that we get Ti, subscript of a 2, oxygen, subscript of a 4. So this means 2 titanium atoms for every 4 oxygen atoms. So this is a good ratio. It is the ratio that we get from this exercise. However, this is not the lowest whole number ratio. Remember, it's a 3-dimensional lattice of trillions and trillions of atoms. So the formula unit is the lowest whole number ratio that we care about to express the fundamental ratio of titanium to oxygen. Since this can be reduced, what we do is we divide both of them by whatever we can, by 2 in this case. So we divide by 2, we get 1. We divide by 2 here, and we get 2. So this is the correct formula unit formula unit is the lowest whole number ratio, also known as the empirical formula. Notice for sodium chloride, we couldn't reduce 1 to 1 anymore. For barium chloride, we couldn't reduce 1 to 2 anymore. We couldn't divide by something to make it smaller. 3 and 2, we couldn't divide by anything there as well. So you just got to be careful that once you do the crisscross, double check and see if you can simplify it any further. And if you can, then you need to do that. All right, what are we going to do next? The last problem we have, I'm going to write some compounds down on the board, and we are together going to try to write down and see, do these form molecular compounds or ionic compounds. Remember, ionic compounds is when you have a metal plus a nonmetal, and molecular compounds, also called molecules, is when you have a nonmetal and another nonmetal, or multiple nonmetals going on. All right, so let's see what we have. We have, for the first one, let's call it B2H6. All right, so this is boron and hydrogen. Boron is on the right-hand side of the table, hydrogen's on the left. However, hydrogen is always counted as a nonmetal. So it's really two nonmetals coming together. So because of that, it is a molecule, or it's molecular. It's molecular. All right, part B. Let's take a look at CH3OH. All right, now we have carbons, hydrogens, and oxygens. And all of those are coming from the right. Carbons, oxygens, hydrogens on the left, but it counts as being on the right, all nonmetals. So because of that, this is molecular. Molecular. All right, let's take a look at part C. Part C, we have lithium right here, and then we have NO3. So lithium is on the left. If you're not sure, go over here and see lithium on the left. And then on the right, we have nitrogen and oxygens. Nitrogens and oxygens over here all on the right. So we have some kind of metal and then some other nonmetals. So because we have metals and nonmetals, this is ionic. This is an ionic bond that's going on here. Let's take a look at D. D is SC2O3. All right, SC is scandium right here. That's a metal. It's in the transition metal area. And then we have oxygen over on the right. So it's metal plus nonmetal, so this is ionic. E. Let's take a look at cesium, bromine. Cesium bromide. We're going to learn how to name these later. Cesium is a metal on the left, and bromine is a nonmetal on the right. The cesium is going to want to lose an electron. The bromine is going to want to gain an electron. Once those charges are those ions have those overall charges, they're going to connect together because of the force there. And so this is ionic as well. Right? And then we have F, which is NOCl. So we have nitrogen, oxygen, and chlorine. Nitrogen, oxygen, chlorine, all three elements from the right-hand side, so these are molecules, or molecular. Right? So ionic is metal plus nonmetal, molecule or molecular is all nonmetals. So we have EF, and now we have G, NF3. Nitrogen, fluorine. So we have nitrogens, fluorines all bonded together, and so because those are all nonmetals, this is a molecule or molecular. All right, and our last one, H, is silver, Ag2SO4. Right, now before we actually do much with it, notice SO4, that seems familiar, right? Because I showed you about the polyatomic ions. SO4 is a sulfate ion with an overall charge of -2. So we're going to learn how to do this later, but basically the -2, that crisscross down here, the silver ion, well, let's just go ahead and do it just for giggles. First of all, let's just say that we have a metal that is right here, and then we have all of these are nonmetals. So right away we know this is ionic. And even though this is not really part of the problem, we'll just pretend that we didn't know what this is. Let's say we're going to attach silver with SO4, right? But SO4 we know exists as a polyatomic ion with a charge of -2. So we just put the -2 right there, and we know that silver from our chart, silver generally likes to form ions with +1 charge. And we just get that from the chart. So there we go. And then we do the crisscross like this, and you get Ag, 2 comes down here, and then SO4, and then you have a 1. So really you have like an invisible parentheses with one of them, so you don't have to write it. So it's Ag2SO4. So We have molecular, molecular, ionic, 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 molecular, molecular, and ionic. Now, the last thing we're going to do before we close the whole lesson out is we're going to remember that ionic compounds are electron transfer from one to the other. Molecules are electron sharing. So we now know that this is going to be electron sharing. This is going to be electron sharing. This is going to be electron transfer. This is going to be electron transfer. This is going to be electron transfer. This one, sharing, sharing, and electron transfer. That's a lot, right? I had to lump it all together. I had to show you how the compounds form. Then I had to show you all the ions so that we can do more advanced problems. And then we had to round out the lesson. That's a lot of talking. That's a lot of doing. So I'd like you to solve these all yourself. Make sure you understand. Follow me on to part 2. We're going to do more in the area of solving these ionic compounds and understanding how they form and how to write the correct formula for an ionic compound. Never forget, after you do the crisscross, to get the subscripts, you have to try to make sure that they're reduced to the lowest ratio, because only the lowest ratio is the formula unit, which is the correct answer for an ionic compound. All right, follow me on to the next lesson. We'll continue to build your skills.